So you're doing some work, especially during this time of online teaching, and that most of the time teachers set deadline to check your power. Completing the work is one, and whether you could submit that on time is another. And that another is your power. In physics, we deal with both of these, work and power. That is why I made this video so you don't respond to physics questions about work and power based on the way you understand these words in an English class. All right? We have specific definitions for work and power in physics. Let's start with the student here, this one, as a system. There we go. And say we also have another system, this red object here, a box. We know that both of these have energy in them. Every object has, isn't it? And that we already covered that energy takes many forms. I'll put some dots here representing energy, but remember, energy is something that cannot be drawn. Just to show you, we have many forms. We have those color dots. Each color can be regarded as a form of energy. Remember that in a system, transformation of energy happens. This form may change to that, this one to this, and so on. But the total energy of the system remains the same. All right? This object or system has an energy. The same way this student has an energy in him. These energies of objects may change. Here, energy may leave the system or this student. In this box, energy may enter the box. As an example, this student say exert a force on the box. Let's write F here for force, and was able to displace the box to here, parallel with the direction of the force, displacement S. We can say that by doing this student has lost some of his energy. He probably feels tired now after pushing the box to this direction. Now, this red box, when pushed, will move, and we can say that it eventually possesses an energy related to motion. Remember kinetic energy? This box gets that. This adds up to its energy. It has just gained energy here. On the other hand, the students lost energy. The box gained energy. Let's put that in symbols. Negative delta E for this student. Negative because it is lost. And positive delta E for the box because it is gained. Now, if these two are isolated, then we say that the students lost part of his energy to the box. Meaning, the energy gained by the box is equal to the energy lost by the student. This equation. And the mechanism, or maybe we can say the mode of energy transfer, is related to F and S, which were caused by the student and the reason the box gains energy. This is where our topic is focusing on. Okay? Let's free some space here. Minimize these ones. There we go. Okay, so this quantity. All right, but before that, let's do a side trip. All right, some dimensional analysis here. Remember the potential energy, mgh. If we are to write the units, kilogram for mass, meter per second squared for g, and meter for height, this kilogram meter per second squared here is defined as a Newton. And therefore, we have a Newton meter as a unit of potential energy. Now, for the kinetic energy, 1 half mv squared, the unit of mass is again kilogram, and the unit of square of speed is square meter per square second. Now, this square here, let's expand. Meter square is meter times a meter. So we have this. Again, the kilogram meter per second squared here is a Newton, leading us back to the same unit. In the SI system, 1 Newton meter is defined as 1 joule. To honor Prescott Joule for his contribution in the study of energy. If you are going to look at the units of the quantities involved here, when the student is transferring energy to the box, F and S, we see, will lead us to a quantity with the unit joule too by multiplying F in Newton and S in meter. This product, guys, is defined in physics as work. And so from here, we can differentiate work from your English understanding of the word. Our work requires a force that could move an object a certain distance along the direction of the force. Also note that the work done by, he did it, the work done by an object is equal to the energy the object lost. And for the box, the work done on, transferred to it, is equal to its increase in energy. Both of these are equal to the product of magnitude of force and parallel distance, or magnitude of object's displacement. Just a simple product, but remember to take a look at F and S first before multiplying to determine the work. Make sure that what you have are along the same line or parallel with each other. Okay? That's very important. The other concept in this video, power, just like what I told you in the beginning, has something to do with time, apart from the force and displacement of the object. Let's erase this once first, all right? Okay? All right, there we go. So for power, let's have an object here being pushed by a force and cover this distance. Let's add another quantity, t, for the time the force was able to complete bringing the object here. I was saying your assignment or homework power in class is on how fast you could complete the work and submit. In a way, it is related to deadlines. It is about time. Similarly, power in physics is also dependent on time. How fast an object was able to complete a work. Power is a rate at which work is done. Equivalently, and because we know that work is simply equal to the change in energy of the doer of the work, or the change in energy where the work is done, we can also say that power is the rate at which energy is transferred. Okay? In notation form or formula, from these definitions, we have P for power equal to W over time. And P equals delta E or change in energy divided by time here. The lesser time you can complete the work or the lesser time you can transfer an energy, the more power you have. Power is inversely proportional to the time. Now, based on the formula W over T or delta E over T, the unit of power should be a unit of work or energy over the unit of time, joule per second. But again, in the SI system, this 1 joule per second is defined as 1 watt. Another name of a scientist with excellent contributions in the study of power. Okay? Simple equations we have here, yes? We can easily calculate quantities based on those. For example, say you have a force equal to 15 newtons and S is 2.0 meters, and the time to bring the objects 2 meters from the starting point is, say, 25 seconds. Let's find the work done by the force, all right? And change the energy in the object and also the power. Work is simply force times distance, and the directions look both rightward, so the product is simply 30 joules. For the delta E, it is also 30 joules because the work done on the object equals the change in its energy. And for the power, based on the formula, should be just 30 joules over 25 seconds, which gives us 1.2 watt. Easy, yes? All right? Bye.